Now we're going to discuss different aspects of group actions. So we're going to fix a group G in a set A, and we're going to assume G acts on A. Sometimes in the literature, this is the way you write that as a shorthand. So this is the shorthand notation for saying G acts on the set A. Let S be a point in A. Then the stabilizer of S is defined to be all elements little g, such that little g dot S is equal to S. So these are the group elements that stabilize the point S. And so as an example, let's pick our example from earlier of the real numbers acting on R to the N. And let's pick X to be the all zero vector first. Well, what does it mean for R to be in the stabilizer? Well, it means that R dot the X vector, in this case the zero vector, is the zero vector. Well, it's not too hard to see that this left-hand side is Rx1 through Rxn. We want that to be all zeros, but x1, xi was 0 for all I to begin with. So it doesn't matter what R you pick, this statement is always true. So R could be anything. And so in this case, the stabilizer is actually equal to all non-zero real numbers. Note the reason why we can't include 0 is because we're working with the non-zero real numbers under multiplication as a group. You can't include 0 in that set because then it's no longer a group, because 0 doesn't have an inverse. Now let's suppose x is not 0, the all zero vector. Well then xi is not 0 for some I. What would it mean for R to be in the stabilizer now? Well, you need R dot x to be equal to x. In particular, you see that Rxi has to be equal to xi. And here, xi is not 0. So we see that R is definitely not 0 anymore. And, well, then by division, we see that R has to be equal to 1. So all the other examples have stabilizer 1. And this is true in any vector space. The stabilizer of the zero vector ends up being all the non-zero elements of the field, and the stabilizer of any non-zero vector ends up just being the multiplicative unit of the field for this obvious reason. Well, maybe it's not so obvious. Yeah, for arbitrary vector spaces, it takes a little bit more work because you have to set up a basis and use coordinates to do this calculation, but the same idea works. Now let's do another example. We already looked at the example of given a subgroup H and G. G acts on the coset space by multiplication by the coset representative. We'll take an arbitrary coset GH, and let's look at the stabilizer. By definition, that's all group elements G, such that G, well, let's say G prime dot GH is actually equal to GH. Well, this one's a bit more interesting because let's try to think carefully what it looks like. Well, we have all G primes such that G prime GH is equal to GH. By definition of cosets, the only way these two are the same coset is if G inverse G prime G is an H. And so we get a condition. It is a bit of an interesting one, so this is about as far as we'll be able to take it, because it actually depends on the choice of G. But it's those elements such that when you conjugate by G inverse, you end up in H. In particular, if you actually choose G to be the identity element, we see that we actually end up with elements in H to begin with. So the stabilizer of the coset H is the subgroup H. Note here that H is playing different roles on each side here. Over here, it's an element in a set on which G is acting, and here it's a subgroup. Finally, we should take a look at that example of conjugation, which I believe was considered example 4 earlier. I mean, you could also look at the example of the symmetric group acting on itself, but that one's actually not that interesting. So let's let G act on itself by conjugation. And so I want to look at this stabilizer of a point. And this is the definition. So this is group elements such that when you conjugate X by G inverse, you get X. We will see this set again in a little bit, so it's a good example to have. Alright, so one of the facts we'll prove is that given a group action, so we have G acting on a set A and an element S in A, the stabilizer, G sub S, is a subgroup of G. And the notation in the textbook is to use this less than or equals to sign as a shorthand for saying this sentence. And there's multiple ways to do a proof. There's 2 different subgroup criteria given in the textbook. And one of the subgroup criteria is that your subgroup, if and only if you're closed under multiplication, H is closed under multiplication, H is the identity of G, and H is closed under inversion. Which means for every element little g in H, G inverse is also an element of H. But another version of the subgroup criterion is that you're closed under what I call left division, which means for any pair of elements, G inverse times H is in H. And I find sometimes that this gives a shorter proof, and so oftentimes I'll use this shorter version. It depends on the example. So sometimes you do the example out using the longer version, and then you look at the notes and see whether or not this actually gives a shorter proof, or if the shorter proof ends up being too complicated to be worth the effort. So sometimes it's worth the effort, sometimes it's not. This is one of those cases where it's better, so that's the approach I'm taking. So I'm going to do this proof now. So H is the stabilizer. So what do I need to do? I need to take 2 elements in the stabilizer subgroup, and I want to prove G inverse times H is also in the stabilizer subgroup, which means G inverse times H acting on S should give me S. That's what I need to show in order to be able to conclude G inverse H is in the stabilizer. So let's try to prove that. Well, by definition of group action, G inverse H acting on S is equal to G inverse acting on H acting on S. Since H is in the stabilizer, H acting on S is equal to S. Since G is in the stabilizer, I can also replace S with G dot S, which is the sneaky trick I'm going to use here. And then because I have a group action, I can move the parentheses over and I have G inverse times G. Because I have a group, G times G inverse is the identity, and because I have a group action, the identity acting on S is S. And so I see G inverse times H acting on S is S. So I do actually get what I need. So let's add in the missing sentence I need here. Thus G inverse H is actually in the stabilizer. Therefore, I actually have a subgroup. So the only part that is non-obvious is this little trick here where I brought the G out of nowhere. And the reason why I did that is so that I could cancel out the G inverse. And the only reason I did that was because that was the easiest way to check the subgroup criterion directly with only one condition. The other approach is to check the three conditions separately like the textbook does. And that's also worth knowing how to do. It's a similar style proof, but it takes slightly more work. And when you do it, you'll see that the three separate arguments actually involve the same ideas I used in this one single proof. So combining them into one makes a shorter proof. That's really no more or less enlightening than the longer version. Mainly because to show closure under inversion, you still have to do this trick anyways. Now we move on to the next definition. A kernel of an action is defined to be the set of group elements. It says that G dot S is S for every S in the ground set A. You can check that this is the intersection of all the stabilizer subgroups, right? Because what does it mean for GS to be equal to S? For a specific S, it means that G is in that particular stabilizer. And this is saying that this element G is in all these stabilizers, so it's in this intersection. And so the kernel is equivalently defined to be this intersection. And it's a standard argument from the undergraduate modern algebra course that the intersection of subgroups is a subgroup. And so we see that the kernel is in fact a subgroup of G. So as a first example, let's look at our action of R scaling real vectors. So the kernel should be this intersection over all vectors, the stabilizer subgroup of that vector. As we saw previously, when you take the 0 vector, the stabilizer subgroup was all non-zero real numbers. And when you take any non-zero vector, you only get the scalar 1. And so, even though this is an infinite intersection, it turns out there's actually only two sets you're intersecting. And this intersection is clearly just the set containing 1, because it's already a subset of this. And so this is the kernel of that group action, and you could check that directly. The only scalar that scales all vectors to be the exact same length they were before is the scalar 1. So, right, the equivalent argument is that this is the definition of the kernel. It's the set of scalars that when you scale every vector by that scalar r, you get that vector back. And it's clear to see from linear algebra that this forces r to be 1. Now we take our example 2 that we had earlier. This is where G acts on the set of cosets by left multiplication. And what is the kernel? It's the set of group elements G, such that when you multiply by any coset, you get the coset back. Now, of course, one way to index coset representatives is to just run through all group elements. That makes this identity a little easier. And then by definition of cosets, these two are equal if and only if this conjugation operation lands in H. So the kernel is all group elements in G such that when you conjugate by all other group elements in G, you land in H, which is a little strange. So if you follow the textbook, they look at a special version of this example to get at the centralizer later. At this point, it's a little weird, but one thing you can show is that if H was a normal subgroup, then this group element G had to have been in H to begin with. And so then you just get something slightly different, which is just all of H. As one final example, we look at the action of group G acting on itself by conjugation, as we've discussed previously. And the kernel of that action would be all group elements, such that G inverse is equal to A for all A and G. This subgroup is actually a famous subgroup called the center of G. A fact I will remark on that the textbook doesn't mention till later, but it is worth noting since we already have the material to state it now, and because we already know about normal subgroups and kernels anyhow, is that this notion of kernel of action and the notion of kernel of a homomorphism are actually the same. So we've already talked about how given an action of a group on a set, this defines a group homomorphism from the group G to the set of permutations on the set A. Well, there is a well-defined notion of kernel of a group homomorphism, and it turns out these two notions of kernel are actually the same. Why is that? Because we define the kernel of an action to be those group elements that fix every element in A. Under our definition of this homomorphism, that means sigma sub G of S is equal to S for every element S in A. But by definition, that means sigma of G is just the identity permutation. But that's the definition of the kernel. The kernel of a homomorphism is a set of elements that your homomorphism maps to the identity element in your codomain group. So a corollary of this is that the kernel is actually a normal subgroup, because we already know that about kernels of homomorphisms in general. And so that weird example we got from example 2 actually is, you can show this and we won't in this course, but that is the smallest normal subgroup of G that contains H. Because you can show every element in H lies in that kernel, and you can prove that the resulting thing is normal, because we just did.